Today we're doing the 2.6 to 2.9 physics course practice quiz for the periodic, and let's start. So first question, it's asking us which is true about the electrostatic paint spray gun. Now for this chapter, I'd rather if you guys memorize it from the book, because that's the best way to actually have all your information. An ionizing electrode charges paint particles positively. This is wrong. It charges them negatively. Electrostatic paint spray guns waste a lot of paint. No, the reason we use electrostatic spray guns is because they don't waste paint. Charged paint particles are attracted to grounded surface. Yes, this is one of the definitions of the electrostatic paint spray gun. So this is true. The spray has to be painted, the surface to be painted is attached to the ionizing electrode. No, it's not. The surface has nothing to do with it. The surface is just a surface. It's just attracting the electrostatic paint. The paint spray gun's advantage is an even distribution of paint. Yes, that's literally the main reason we use it. Moving on. Which of the following best describes an electric field? So an electric field is a vector. It's a vector quantity, and its formula is let me just make sure of the formula. So yeah, the formula is E equals F over Q0. So let's start reading. It has a magnitude and a direction. If it's if it's vector, then it has a magnitude and a direction. So it has a unit, you could say. It's specific on direction. Scalar quantity, no, it's a vector. The magnitude of the field is any point. The magnitude of a field at any point is the work per unit charge. No, it's not. This isn't the correct formula. Is best described using charged spheres. No, it's not. The magnitude of the electric field is electric field equals force over charge. Yes. And by the way, the best way to describe it is using lines, not spheres. Okay, here we need to memorize the parts of the gold leaf electroscope. This is the plug, and it's insulating. The case is anything on the outside. The conducting rod is this thing, and this is a knob, and this would always be the gold leaf. Okay, so here we have an electroscope. If you bring, which is the device we just saw, by the way, let's draw it first. If you bring a positively charged rod, it's used to charge a neutral gold leaf electroscope. If you bring a positively charged rod, this is gonna move all of its positive electrons here. All of its negative electrons here, which means the positive ones are gonna get pushed down the rod and to this. And if this is positive and this is also gonna be positive, the leaf is gonna repel away from the rod, so it's gonna diverge from it. So let's say now you bring another positively charged B with a charge greater than A. What's gonna happen if you bring more electrons down the rod? More protons down the rod, more positive charges down the rod. If it gets stronger, then the force of repulsion between them is also gonna get stronger. If they're gonna get stronger, the leaf will diverge away from the rod. Now, you bring a third rod, but this time it's not positively charged. In the same electroscope, by the way, it's like these are going one after in each other. And then you bring a negatively charged one with a magnitude greater than A and B combined. So now it's diverged further away from the rod. You bring a negative charge. Since now the rod's positively charged, what's gonna happen when you bring the stronger negative charge is the negative charge is gonna keep adding charge till it cancels out all the positive charges, so it becomes neutral. So when it becomes neutral, it's gonna fall back to being straight, like this isn't gonna diverge, it's gonna fall back, and then the minute you have extra positive charges, it's gonna diverge again. So let me explain it more. So here's your rod, and now it's diverged like this. You bring the negative charges. When you bring negative charges, here you're gonna have positive charges. We originally had positive charges all down the rod and the gold leaf because of the other first two experiments. But now it's gonna get changed by negative charges, because now you have the positive getting attracted to the rod and now negative moving all down the rod. So now we're gonna wait for the point where all the negative charges cancel out all the positive charges. It's gonna become neutral. When it becomes neutral, this is gonna go like this, but then when you get a singular extra negative charge more than the positive, it's gonna repel again and go back like this. So the leaf will fall and then diverge again. Moving on. Okay, so in a simple Van de Graaff generator, when the motor on the lower insulating roller acquires a negative charge, because look, here's your thing, and then you have a roller and it's connected to another thing. When it's rolling from the rubber, it's gonna get a negative charge from the rubber belt, which means leaving the top part which builds up a positive charge going back up. And then the two brush assemblies, by the means of the two brush assemblies, the negative charge which is down here is drained, which is earthed, leaving only positive charges up here. That's it. Okay, so this is an electrostatic precipitator. This chapter, read it from the book. So this is a positively charged grid, and these are neutral metal plates. These are smoke particles. And we know that neutral conductors and neutral insulators attract all charges. Because they're neutral, they'll just attract anything that comes towards them. So positively charged ions. Moving on. Okay, here we have field lines. So diagram below shows us two electric fields, the 2 points. So we can tell, what can we tell about this electric field? You have two forces, but they're not attracting each other, they're repelling each other, as you can see here. So if this was positive and they're repelling, what does this be? A positive charge. That's the first part. Now the electric charge is 0 at, you need to go to the point which is here. Between the two repulsion forces, there is no electric field. It's passing around it. It's not going towards point 4. So that's where there's 0 magnitude. But the point where there's the highest, which is the third part, which is the strongest electric field, is this. It's the one closest to the point charge. Now let's move on. Okay, so you have a force acting on a 30 nanocoulomb charge at a certain point in space is 2.4 micronewtons. So let's bring back our equation. E equals F over Q. So we need to find the electric field E. We have F and we have Q. So F is 2.4 micronewtons. We need to convert it to what is called normal newtons. So 2.4 micro means times 10 to the power of -6 over the charge, which is plus 30 nanocoulombs. So 30 times 10 power, nano means -9. Once you divide these two by each other, let's see, I have a calculator somewhere. Wait, sorry, my bad. 2.4 times 10 power -6 over 30 times 10 power -9. Wait, what? Let me see, there's something wrong because I solved it yesterday. It was right. Yeah, the calculator was wrong. Anyways, 2.4 times 10 power -6 over 30 times 10 power negative 9. You can solve it on your calculator. You should get 80. I solved it right now on a different calculator. I got 80. I don't know what's wrong with this one. Maybe it's in radians. Anyways, that's how you solve for this one. Now moving on. Okay, so here you have two parallel oppositely charged plates. The left one here, this is negative and this is positive. They want you to drag and drop the correct direction of the field between these plates. It's gonna be this direction, because always it's gonna go from towards the positive to the negative. It's never gonna go from the negative to the positive. And it's in straight lines because they're opposite. Yeah, it's a line to a line, so they're gonna be opposite and like this. See, they're oppositely charged plates, parallel. Now, at these 2 points A and B, between these plates, the electric field A on point A and the electric field at point B, how do their magnitudes compare? Always, when you have like this, they're always gonna be equal. And if the force on a charge negative Q is placed at point A is FA, and the same force is placed on B, how are they gonna be? So electric fields and forces are gonna be equal to each other, same. Okay, so you have a manufacturer, and when they're working with computer chips, they must take care not to become charged. So any electrical discharge will destroy expensive computers. So the benches that the chip manufacturer should sit on should be made of a conductor, a metal. That's the only conductor in the option, so metal is your answer. It should be made of metal because you want to ground it. You want the electric charges to pass through it and go towards the ground and earth it. Such benches would ensure the earthing of their bodies, so they don't charge the chips. Okay. So for this question, you have, it's asking you what's the charge of each particle. So here we have two S and T, they're attracting each other. So, and we also told you that it's always going to go from positive to negative. So making S positive, it's going to the negative. So S is positive, T is negative. Particle U and V. So look, it's in the nature. For this one, you need to know that, first of all, you can tell that they're repelling because they're not going towards each other. So they're both the same charge. They're both going to be either positive or negative. To know, this is how you know, look. So in the nature of positive charges are always going to go away from the source. This is your source. It's always going to be facing away from it if it's positive. If the arrows were going towards it like this, then they would be negative, but it's not. It's going away from it, so it's positive. Now, here you have an electroscope, and shown below with a positively charged glass rod. The gold leaves spread away from each other. When another charged rod is brought close to the metal knob, the gold leaves will be close together. So if positive made them far from each other, then what's gonna make them close? Negative. And that's it for this quiz. Hope you understood. Have a great day.